We've already seen that gases have particles that do not appreciably interact with one another. So these gas particles, they have a lot of empty space between them relative to the size of the particle. Now, if we compress the gas and we remove that empty space, or if we decrease the temperature of our gas, then we start to have some interactions between our molecules or particles. And when we start to have those interactions, then our gas will start to condense. And when we condense, we're starting to form a liquid. Now, at the same time we have condensation, we're going to have evaporation. So condensation is going from a gas to a liquid, but evaporation is going from a liquid to a gas. Now, these particles are going to start interacting with one another by using our intermolecular forces. Recall that our intermolecular forces are dispersion forces. We have dipole-dipole interactions, and we have hydrogen bonding. Hydrogen bonding is a special case dipole-dipole interaction. We're not going to look at the ionic interactions in my courses. Now, when we have this gas that condenses into a liquid, it gives off energy. So we're going to have decreasing energy. On this side, we're going to make just this little graph. We also have our temperature. So we have a decreasing temperature, we have decreasing energy as we go from a gas to a liquid. So condensation, or going from a gas to a liquid, is an exothermic process. So as we go this way, we are exothermic. We are giving off the energy. As we go this way on the graph, we're going to be endothermic. That means we're going to be absorbing the energy. So it takes energy to evaporate liquid, and it gives off energy when we condense our gas to our liquid. Many of the properties we're going to talk about with liquids are governed by their intermolecular forces. One of those properties is viscosity. Now, viscosity is formally defined as being the resistance to flow. But we can talk about viscosity, and this is a temperature-dependent property. There we go. A temperature-dependent property, because a more viscous liquid is going to be something like honey. So honey, the particles or molecules in honey have a lot of interaction. They're very long chain hydrocarbons and some sugars. You got your glucose and your fructose. So we have these large molecules, and they have a lot of interaction between them. And because of all of that interaction, they don't necessarily want to let go of one another, because our liquid molecules, I'm just going to draw water out here. Our liquid molecules are not permanently bound to their nearest neighbors. In fact, they're loosely bound to their nearest neighbors, and it's the viscosity that tells us how loosely or how tightly they are bound to their nearest neighbors. So when we have something like honey, and it has a lot of interactions, it doesn't want to let go of its nearest neighbor, then what we have is a very viscous liquid. So as I'm drawing out the water interactions here, you can imagine, regardless of what the molecules are, these dotted lines, which I'm just going to highlight just to try to call attention to them, these are our intermolecular forces. This is what's holding our molecules together. So the stronger those forces, the stronger those interactions, and as we talked about in the intermolecular forces video, you can have dispersion forces that are fairly strong with one another, and that's typically going to be molecular weight dependent. The molecules in honey have high molecular weight, so they have a lot of these dispersion forces. And so they don't necessarily want to let go of one another. And because they don't want to let go of one another, they're not going to pour very well. They're going to be a viscous liquid. They're going to hold on to one another rather than let go. Now, if we heat that honey up, it's going to flow a lot better. And that's why viscosity is a temperature-dependent property. Typically, we say the greater the viscosity, the more resistance to flow, the thicker or the more difficult the liquid would be to pour. Now we also have a property called surface tension. And the surface tension of a liquid, so if I draw a surface here and pretend that my water is in a container, the surface tension of a liquid, and I'm just orienting them this way, it doesn't have to be oriented this way, but surface tension is going to be the attractive force of the molecules on the surface of a liquid to their next door neighbors and to the molecules below them. That's the surface tension. So again, the stronger the intermolecular forces between the molecules themselves, the greater the surface tension. Now, if we give this surface a little bit of energy, and that energy could simply be room temperature, it doesn't have to be much, that increase in energy will allow some of these surface molecules to escape from the liquid phase into the gas phase. Now, some of these gas molecules will also then cool to reform the liquid. And this is what's called a dynamic equilibrium, when you have condensation and evaporation occurring at the same time, at the same rate. That's your dynamic equilibrium. And that's found on this graph on this plateau. And I'm going to connect my gas and my liquid now on a plateau that's supposed to be parallel to the axis. Now we can increase the rate of vaporization by increasing the surface area of our liquid. So if you have, say, if you spilled, 3 ounces of water and it covered an area of 2 square meters, that is going to evaporate much faster than 3 ounces of water in a glass. And that's because more surface area has more of these molecules on the surface that can potentially move up to the gas phase. When it's in the glass like this, the body molecules, the molecules within the liquid, are interacting with molecules all the way around it, 360 degrees, whereas the surface molecules are only interacting with the molecules next door and below it. So they take less energy to be released into the gas phase. Now, liquids that evaporate easily are called volatile liquids. Volatility is a relative term, really. Usually we use water to describe volatility. So then liquids that do not evaporate quickly are called non-volatile. So again, that's relative. We usually use water to relate it, and rubbing alcohol is an example of a more volatile liquid. Now that's more volatile than water, and then motor oil is virtually non-volatile. We also have a property called vapor pressure, and the vapor pressure of a liquid is going to be the partial pressure of the gas in a dynamic equilibrium with its liquid. So here, where we have condensation and evaporation, we can measure the vapor pressure at this point. Now, the vapor pressure increases with an increase in temperature and a decrease in intermolecular forces. This is a dynamic equilibrium. Again, we have both condensation and evaporation occurring at the same time. Vapor pressure is independent of the surface area. And that is because an increase in the surface area at equilibrium, we're still going to have an equilibrium. So it equally affects the rate of evaporation and condensation. Now, if we have a liquid in an open container and we give it some energy. So now on my graph, I'm going liquid and I'm giving it energy this way. And I give it that energy. I'm giving it thermal energy to increase its kinetic energy. And when the vapor pressure of a liquid is going to be equal to the pressure above it, the energy of the body of the liquid is enough to break into the gas phase. And that is called boiling. That is the action of boiling. So that's what's occurring right here. Now, when you boil water on the stove, and we probably all know that water boils at 100 degrees Celsius. That's kind of one of those things that people come into this class knowing, and that's at 1 atmosphere. When you have a pot of water boiling on the stove, the bubbles that are forming, and I'm not talking the little bubbles around the edge of the pot, but the larger bubbles that go from the bottom of the pot to the top, that is a bubble of gaseous water from the body of the liquid that is trying to escape into the gaseous phase. Now, boiling water will always be 100 degrees Celsius. So if this is a water curve, this will always be 100 degrees Celsius. It will not increase in temperature. You see, I'm going up here. It will not increase in temperature until all of the liquid is gone. Now, steam burns hurt worse than boiling water burns. And the reason for that is not only is boiling water 100 degrees and steam can be much higher, but it gives off energy as it condenses. And if it gives off that energy on your skin as it condenses, that can hurt an awful lot. So remember that condensation is an exothermic process and evaporation is an endothermic process. Now, I'm going to draw this diagram the other way. So if we still have over on this side, we have our increasing temperature. And over here now I'm going to make it so that energy is increasing. So that puts the gas phase up here. Then I have a point and a plateau. Then I have a point and a slope. So this is my liquid phase. This is my gas phase. And here I have my condensation. I have my evaporation. And I have active boiling occurring here. So you may see this as boiling and condensing. You may see it as condensation, evaporation. All these are the activities that are occurring on this plateau. Now, generally speaking, we call this point here the boiling point. And we call this point here the condensation point. That's because as we move from the gas phase down to the liquid phase, we condense. And as we move from the liquid phase up to the gas phase, we start to boil. That's why those points are given different names, although they have the same temperature. We have our exothermic processes going this way, because exothermic is giving the energy back. This way is endothermic, and we are adding energy to it. So you see, going from a liquid to a gas is endothermic. Going from a gas to a liquid is exothermic. Now here we're talking about some heats. So this is the energy increasing. This is heat added. Now we have, for a liquid, we have what's called the heat of vaporization. The heat of vaporization is the amount of heat that's required to vaporize 1 mole of a liquid. So it's also the heat required to condense from a gas to a liquid. It's just the other direction. So they are equivalent values. Now the heat of vaporization is a temperature dependent property, because the higher the temperature, the easier it is to vaporize. So if I had, say, 70-degree water and I had 1 mole, that's going to require less heat energy added than 20-degree water, 1 mole. Because we're talking about being here versus being here. So the energy needed is going to be this distance versus this distance. So you see, this energy distance is going to be greater than this energy distance. So this is a temperature dependent quantity.